All right, let's jump straight into this explainer with a notoriously tricky exam question that trips up countless students right out of the gate. Take a look at question 54. It asks exactly why zinc and cadmium seemingly break the rules of the D block and refuse to show variable valency. It is a classic trap. We see these elements sitting right there in the D block, and we expect them to act like all their neighbors. But they just don't. Well, today we're going to crack exactly why that happens.
Welcome to the explainer. If you have ever felt totally overwhelmed by the sheer volume of exceptions, colors, and complex reactions in this part of inorganic chemistry, you are definitely not alone. It is a lot to take in. But today, we're deciphering the source material together to transform these intimidating memorization-heavy D and F block elements into pure visual logic. You'll be tackling these exam questions with absolute confidence in no time.
We're using a highly targeted concept-to-combat approach today. We'll decode 6 high-yield themes: cracking the D and F blocks, the variable oxidation code, color and magnetic properties, key compounds and permanganate highlights, demystifying the F block elements, and finally, locking in our final exam strategies.
Section 1. Cracking D and F blocks. What actually makes a transition metal?
Let's see how this builds your core understanding. Because as we saw with zinc, mere geography on the periodic table just isn't enough. The absolutely crucial point is right here in the official definition. It is all about having an incompletely filled D subshell. That is the ultimate cheat code for understanding their unique properties. If that D subshell is completely full, meaning it's got all 10 electrons packed in, or if it's completely empty, the element literally loses its transition superpowers. It has to be partially filled, either when it's just sitting normally in its ground state or when it forms a common ion. Now, what's really fascinating is how examiners use that exact definition against us. Check out question 32 from our source material. It asks why all zinc plus 2 compounds are white. When you think about it, the answer is directly tied to what we just talked about. Zinc has a D10 configuration. That means its D subshell is completely stuffed full. Because it's full, there's just no room for electrons to jump around and absorb light. So it technically doesn't transition, and therefore it completely lacks color. Make sense, right?
Moving into Section 2, the variable oxidation code. Why they change their numbers.
Okay, let's decode one of the most famous, and honestly sometimes frustrating, superpowers of the D block. Their ability to show multiple oxidation states. Why does manganese go all the way up to +7, while S-block elements are stuck at +1 or +2? Well, if we look at this specific problem, question 46 from the source, it brilliantly highlights the chemical secret. To show variable oxidation states, transition metals don't just use their outermost s orbital electrons. They dip into their inner n-1 d orbital electrons too. Why? Because the energy gap between that outer s shell and the inner d shell is incredibly tiny. The electrons from both subshells are essentially right there, available to jump into chemical bonds. Notice the pattern here when we put them side by side. On the left, we have our rigid S and P block elements. They have fixed valencies. They're predictable. But on the right, look at our D block elements. Thanks to those readily available D electrons we just discovered, they have highly flexible bonding. This variable valency is exactly why transition metals make such fantastic catalysts in industrial reactions. They can easily lend and borrow electrons to just speed up chemical processes like crazy.
Up next is Section 3, color and magnetic properties. Painting with electrons.
Let's dive into the most visually stunning part of inorganic chemistry, color and magnetism. Now, this is highly tested, and there is a massive trap hiding here that we really need to watch out for. You might logically think all color in the D block comes strictly from those partially filled D electrons jumping around. A process called a DD transition. But take a look at question 4. It asks you to identify which species owes its color to charge transfer. This is the trap. Some compounds, like the intensely purple permanganate ion, actually have a D0 configuration. They literally have no D electrons to jump. Instead, they get their deep, vibrant color from an entirely different phenomenon, where an electron temporarily shifts from the oxygen atom right over to the metal.
Locking this pattern into your memory is your ultimate rapid-fire weapon for immediately eliminating wrong answers on multiple-choice questions. If a complex is paramagnetic and colored, it's almost always due to unpaired D electrons. If it's diamagnetic and completely colorless, well, those D electrons are either perfectly paired up as D10 or completely empty at D0. But if you see a complex with deep, intense color, like the dark purple of permanganate or the bright orange of dichromate, and you know it has 0 unpaired electrons, boom, the answer is charge transfer.
every time. Section 4. Key compounds. Permanganate highlights. The heavy hitters.
All right, now we are facing the boss level of the D-block chapter, multi-stage reactions. These source questions prove that examiners absolutely love testing your knowledge of how heavy-hitting compounds like KMNO4 behave, especially in acidic environments. On the left side here, we see question 50 asking specifically about what happens when KMNO4 mixes with hot oxalic acid. And on the right, a match-the-column question testing its properties, like how it decomposes in sunlight. The takeaway here is that we can't just memorize the balanced equation. We actually have to understand the kinetic story of what is happening inside the beaker.
This step-by-step breakdown maps perfectly to that specific exam question. When KMNO4 mixes with hot oxalic acid, the initial reaction is painfully slow. Honestly, it barely looks like anything is happening at all. But as the reaction slowly proceeds, it produces Mn2+ ions. And here is where the magic happens. Those newly formed Mn2+ ions act as an autocatalyst. The reaction literally creates its own catalyst. This means the reaction speed isn't constant at all. It hits fast forward and suddenly decolorizes incredibly fast.
Section 5. F-block elements demystified. Journey to the inner transition.
So let's shift our focus to the very bottom of the periodic table. You know, those two rows floating down below, and demystify the F-block, affectionately known as the inner transition elements. This brilliantly illustrates exactly how the exam is going to test us on this. Look at question 11. It gives you raw electronic configurations and asks you to categorize them. To survive this kind of question, we have to look at the configuration and play detective. We are looking to spot if that very last differentiating electron is burying itself deep down into the N-2 F subshell.
By comparing them side by side, the core structural difference becomes entirely obvious. Over in the D block, the last electron enters the N-1 D subshell, leaving the two outermost shells incomplete. But in the F block, they're hiding their active electrons one layer deeper. That last electron dives into the N-2 F subshell, which means an inner transition element actually has its three outermost shells incomplete. It's beautifully logical when you think about it. It's exactly like a chemical Russian nesting doll.
And finally, Section 6. Final exam strategies. Winning the chemistry game.
Okay, let's wrap this up by crystallizing everything we've just visually decoded into actionable, high-yield exam strategies. If you can lock these 4 rules into your memory, you'll be able to navigate almost any trap the examiners set for you. Remember, zinc, cadmium, and mercury with their full D10 shells are traps. They are not true transition metals. Unpaired d electrons are your primary source for color and magnetism. Always, always double-check intensely colored compounds like KMNO4 for charge transfer. And finally, remember that the tiny energy gap between the NS and the inner d orbitals is exactly what unlocks their variable valency.
I'm going to leave you with this provocative thought to test your new logic. We know from the source material that D-block metals make great interstitial compounds because they trap tiny atoms like carbon or hydrogen in their crystal lattices. But considering what we just uncovered about the F-block hiding its active electrons an entire layer deeper, how might that deep, shielded electron architecture change how they interact with trapped atoms? Keep questioning the underlying patterns like this. Rely on the visual logic of the orbitals we explored today, and the rest of this subject will completely open up for you. Thanks for joining me on this explainer, and good luck out there.